This drone accelerates from 0 to 60 in a blink of an eye, and its motors are spinning at 3 times the speed of an F1 car engine, while consuming more power than a standard e-bike each. Today I'll show you how these drone motors work, I'll make my own ESC, and then I'll put it in a drone and fly it. Let's start simple. Here's our motor. The stationary part we call the stator, and the spinning part we call the rotor. In brushless drone motors, the rotor contains the magnets, and we call it brushless because normal DC motors need to energize the rotor using brushes, which will wear out over time. We can draw the rotor as just a magnet, and our stator can be drawn like 3 coils around it 120 degrees apart. So we call this a 3-phase motor. When we run current through a coil or a phase, it creates a magnetic field, and we can control the direction of this field by controlling the direction of the current. By turning these coils on one by one, we can create something called a rotating magnetic field. The rotor magnet will then be attracted to this rotating magnetic field and follow it and start spinning. This is actually how any 3-phase motor works on a basic level. The maximum force generated by this motor is when the magnetic field of the rotor is perfectly perpendicular to the spinning field of the stator. It's like this analogy, when you can apply the most torque on something if it's perpendicular to the force that you're putting on it. So ideally we want to keep these fields perpendicular like this to get the most torque, but for that we actually need to know the speed of the motor, which I'll talk about later. Okay, so we can spin this rotor by turning on these coils in a certain sequence. Most drone ESCs use 6-step commutation for this. This is basically just a 6-step process of turning each coil on and off. As you can see, this means our magnetic field is not actually rotating very smoothly, but in 6 steps, which does cause something called torque ripple, but for these high RPM drone motors, that is okay. One thing though is, in order to know what speed we need to rotate our magnetic field, we need to actually know the physical speed of the rotor. If we try spinning the field too fast or too slow, that could lead to desyncs where the rotor stops following the magnetic field of the stator. How we do this is actually really cool. You might have noticed that in 6-step commutation, there's always one phase that is not being powered. We call that phase the floating phase. You see, if a motor is spinning and it's not being powered, it turns into a generator. It'll generate a voltage with a frequency according to its actual speed, and we call that voltage the back-EMF. We can now check when this floating phase does something called a zero crossing, and then commutate the stator 30 degrees later. 30 degrees is in this case a theoretical value, but we're really switching a coil, which is an inductor, and an inductor resists changes to current, so the magnetic field strength will not immediately be at a maximum. So in order to get peak magnetic field strength at 30 degrees after a zero crossing, we can use something called timing advance, which is basically just switching the inductor a little bit earlier than expected, like 15 degrees. Too much of this timing advance though increases torque ripple. In order to read this back EMF, there's actually a connection straight from the motor back to the processor, which then uses a fast comparator to detect a zero crossing. On my first board, I actually forgot to add the virtual start point to this network, which is the other side of the comparator, and the motor was just twitching because it had no idea how fast the motor was going. After adding it manually with some extra resistors though, it worked fine. 40?
1 amp, 1.3 amp, 1.4, 1.5.
I want to check the motor temperature really quick. But hold up, before we can make an ESC, we need to understand how to make it from real components. So here's the schematic for my AM32 ESC. It looks very complicated, but it's actually not that hard. To switch the phases on and off, we can use this 3-phase half bridge with 6 N-channel MOSFETs. This way we can turn any phase on or off. N-channel MOSFETs are ideal for this because they can switch very fast and handle a lot of current. But to control MOSFETs, you need a gate driver. This is for 2 reasons. In order to switch a MOSFET fast, you need a lot of current to charge the gate capacitance. And our microprocessor can really only deliver a couple of milliamps. This driver can do 1.5 amps. The other reason is more complicated. In order to switch a MOSFET, the voltage at the gate needs to be higher than the voltage at the source. We call this VGS, which needs to be higher than V threshold. For these bottom three MOSFETs, that's no problem since the source is always connected to ground. But for these top three MOSFETs, the source is connected to the motor phase, which can actually have battery voltage on it. So we need a gate driving voltage higher than battery voltage. To do this, we use bootstrapping capacitors. When the bottom MOSFET is turned on, we charge this capacitor right here. And when we want to switch the top MOSFET, we bootstrap our gate switching voltage up higher than the battery voltage using this bootstrapping capacitor so that we can switch our top MOSFET. And then finally, to control the switching in the brain of the ESC, we have a microprocessor, which in this case is an AT32. This controls the gate driver and also measures the back-EMF for zero crossing commutation through this resistor network. So now it's time for a much more challenging 4-in-1 design. In order to put in a drone, we need 4 ESCs for 4 motors. So here it is. One side contains the logic with the 4 gate drivers, the 4 microprocessors, and all of the feedback resistors, and also some voltage regulation to supply the low voltage system. The other side has all of the high current MOSFETs and a large capacitor bank to supply the large transient current and also to filter out spikes on the voltage supply. There's also a shunt resistor here and a current amp for sensing current. After a couple of weeks of designing, I ordered the boards and honestly, I was not expecting these to work first try. But anyway, I flashed the AM32 bootloader using an ST-Link.
Well, dat is één.
Sick.
And then I flashed firmware to each of the 4 ESCs. And it just worked. So I guess it's time for some test testing. So I put in this half-built drone and I'm gonna do a full throttle test. It got pretty hot, but it held on, and I think it's about time we finish this drone and give this ESC a real test. The drone I'm building here is a pretty standard FPV drone. It has my ESC, controlled by a standard flight controller, a DJI O4 system for video, and Express LRS receiver for receiving. It's a 3-inch drone, which is not very big, and it uses these 1408 motors at 3700 kV. On success, this thing is gonna draw some real current.
Oh!
Yeah.
This is my friend Yuna, and he also flies FPV drones, so we're about to go fly right now, and I hope you have fun of our little vlog.
We are charging the batteries.
Yeah.
Look. Die datums heb jij tijd, kan je nog vast te maken. Nee, wacht, ik zit aan het filmen.
Dag Peter. And in perfect me fashion, I forgot to record any footage on the drone itself, so you're just going to have to enjoy this POV footage and some phone recordings. Yeah, whoops. Hey! I also tried flying this drone, which is a custom built thing, and I promptly then did this, so that will be for a later video. Okay, now I'm going to do the real test. I'm just going to hold down the throttle 100% until the battery dies and see if the ESC overheats. I don't know if it'll survive this. Tot 80% throttle, nu ga ik echt gewoon gaan. Ik ga flyby doen, wacht hè. Oh, we lopen. Oh shit, after 90 seconds, the battery is dead. And the drone lives. The drone lives. Wait.
I am eating Easter eggs.
Easter egg?
Yes.
Oh. Can I have some?
No.
Oh yo! Peter when he gets new batteries.
Mag ik?
Ja. It's de FPV van. Wat ben je aan het doen?
De schoenen moeten aan doen.
Ja.